Hello folks. Well, in the last session we got to the point where our little routine here, the setup routine, was working. All the registers were being set as they should be. We checked to see that the timer was counting as it should and that it did reset when it reached the timer counter compare register. So that was all working, but we said that before we could actually do anything with it, we needed an interrupt. Now, before you can use an interrupt, you have to have an interrupt table, or what we call the vector table. And there it is. There's the vector table. I would suggest that you make a copy of this. I'll put it in the description below, and just keep it somewhere on your disk so that if ever you're starting up a program, you can just copy this in as a template, because all of the reasons for interrupts are in here. The reset is an interrupt that happens if you raise a signal on pin 1, that's the reset pin, or otherwise if you simply switch the chip on, it'll start here. Interrupt 0 is pin 7 on the chip, and if you raise a signal on that pin, then it will cause an interrupt. In the soft start mechanism that I made for my saw, that's the interrupt that I used every time the mains crossed 0. It caused a 5 volt on this pin, and that's when the chip started its timing run. Pin change interrupt. This is if any pin changes state. So maybe pin 5 goes from a 0 to a 1. That'll cause it to do it. And there's all sorts of stuff you can set up to do with this. You've got to go through the data sheet. Timer counter 1 compare match A, and timer counter 1 compare match B. A and B are the two compare registers, and this is timer 1. Remember that we're dealing with timer 0. Timer counter 1 overflow. If it gets up to 256 and then wraps around to 0, it'll give an interrupt. But we're not going to use that interrupt. Here's the timer 0 overflow, but we're not going to allow it to overflow, so we don't need that. EEPROM ready. I haven't actually played with the EEPROM. You would need to go into the data sheet if you want to use the EEPROM. The analog comparator, I don't know what that does, but it's obviously something to do with the ADC circuit. ADC conversion complete is pretty self-explanatory. Timer counter 1 compare match B, we talked about that. Timer counter, this is the one that we're going to be using. Remember, when it compares with the output compare register A. So here we've got timer 1 counter 0 compare match A, and it'll take that interrupt. And then the others we aren't using, but compare match B, that's the other output compare register. The watchdog timeout is a potentially useful thing. I haven't used it myself yet, but normally in your idle loop, or in your program is normally running around a loop of some sort, and somewhere in that loop, if you set a count into the watchdog timer, then it'll start counting down in the background. It's a bit like the timer that we've been setting up. So the watchdog timer starts counting down, and then if your program is running properly, it'll run around its loop and it'll get back to the same point again, and it'll reset the time in the watchdog timeout. But if something goes wrong and the watchdog timer actually times out, then it'll cause a reset and it'll come up here. USI is the serial interface, and we've got a start and an overflow, and there again I'm afraid I haven't used the serial interface, so I can't really talk about these. This is when we get our interrupt here, it will come to this. Now you notice that it's an R jump. If you've done any C programming, you'll know that C specifies that a vector is a pointer. So a vector contains an address. In this vector table, it's really a jump table. It doesn't contain addresses, it contains jump instructions. So remote jump, and it jumps to wherever you want it to go to. In an interrupt routine, the first thing that you do is save the status register. And there's no logical reason why it should be so, but it seems to be convention in the forums that I've been watching that you save it into R15. There's the status register up there, and you know what's in it. It contains the results of the previous operation. Now, remember that this program, this interrupt, gets called, I wouldn't really say haphazardly, but as far as your program is concerned, it can happen at any time. Your program is busy doing something, this timer reaches its compare setting, and it interrupts. Now, your program might be executing a comparison between two registers, and it has set something into the status register here, and you're about to act on that comparison, but before you get a chance to act on it, you get an interrupt, so it comes up here. So you really need to save the status register and to restore it again before you leave the interrupt. There are a few instructions that I've put in just for demonstration, and I'll talk about those later on. But the guts of what this does is it sets register 22 and this value here. Now I've decided to use register 22 as a flags register, and at the moment I'm only setting one flag in it, and that is at the end of the millisecond. So remember that all of our setup was to make the timer run once every millisecond. We should get an interrupt. So it's going to set this bit to say I've got to the end of my millisecond. Then down in the idle loop we're going to test that, and we'll reset it so that it's ready for the next millisecond, and we're ready to recognize the next millisecond. Now pay attention to this, because I'm going to test you on it. There are two instructions that I found very confusing, and you might be a lot cleverer than I am. In fact, you probably are, but you also may find them quite confusing. And it's SBR, CBR, which are two complementary instructions: set a bit in a register or clear a bit in a register, and skip if a bit in a register is set, SBRS, and skip if a bit in a register is clear, SBRC. So we're just going to do a little exercise with these instructions. So at the moment R25, as you see, has a value of 0. When I execute this first one, it's going to set these 4 bits here. It's not doing a load immediate. It is not simply writing 0 fox into the register, although it's going to look like that. It doesn't matter what it had in the top nibble there. It will only set the bits that are set here. So those 4 bits, the fox, it will set those. Execute, and you see that R25 has gone to 0 fox. Now I'm going to do a clear a bit in a register of 25, 0, 4. Is that going to do anything? Well, the fox is an 8, a 4, a 2 and a 1. So the 4 will get cleared, and when I execute that instruction, it goes to 0 baker. When I set the 50, the 0 will not affect the bits that are already in there. So the baker will stay a baker, but 5 will get set in the upper nibble. There you see it. And now I'm going to do a clear bit register of 1, 1. So have a little think about what that'll do. What is going to be the result of this? How is this 5 baker going to change when I clear bits 1, 1? What do you reckon? Let's do it. Goes to 4A. So the lowest bit of the upper nibble and the lowest bit of the lower nibble were cleared. Now these instructions here can set multiple bits or can clear multiple bits in a register. So every time I use them, SBR and CBR, I use 0x and I say what bits I'm talking about. The next two instructions, this is skip if a bit in a register is set, and this one is skip if a bit in a register is cleared. but they're only dealing with one bit. So skip if the bit 3 in R25 is set. Is it set? Well, R25, bit 3, bit 0 is 1, bit 2, bit 3. So yes, it is set. And it should skip now the first no-op and land on the second one. Yep, that's what it did. Then it goes to the next instruction, skip if a bit in a register is cleared, and it's talking about R25 bit 6. Is bit 6 set or clear? The bits are 0, 1, 2, 3, and the upper nibble is 4, 5, 6, and 7. So 6 is set, it's that 4. It's going to skip if the bit is clear, and it's not clear, it's set, so it's not going to skip. So it goes to the next no-op. It doesn't skip it. Okay. I hope you found that instructive. Okay, this is all the setup that we did to get it going. Now, down in the idle loop, there's the final set interrupt. Here's my idle loop. I think that label said junk before, but it says idle now. Now, we're going to do a test. Should we do an SBRS or an SBRC? SBRC, skip if a bit in a register is cleared. SBRS is skip if the bit in the register is set. You can see that the register can be any register from 0 up to 31, and the bit can be any bit from 0 to 7. So at this point, I really would like you to pause the video and just have a little think about two instructions. Hang on, before you pause it. We're going to need to do this test, so we're going to say skip if register 22, and what goes in here, is this going to be a 0 or a 1 or what? If this condition is met, it will skip this instruction here, the R jump. If the condition is not met, R jump will go back to idle, which is effectively this instruction. So it'll just keep running around this little two instruction loop until that bit gets set by the interrupt. When it does, we'll come down here and we'll say clear a bit in a register, and what should go in here? There again, go to the instruction set and look up CBR. Right, did you figure it out? Well, I'll tell you what I got. There's the first instruction. It's got to be a skip if the bit register is set, because the interrupt is going to set that bit. And it should be bit 0, not bit 1. Why? I made a little diagram up here. Here's the register. There's bit 0, and the value of that bit is 1. The value of bit 1 is 2, the value of bit 2 is 4, 8, 10, 20, 40, and hex 80. You could also write those in decimal, of course. 1, 2, 4, 8, 16, 32, 64, 128. The way that the definitions are done in the definition file, they talk about bit numbers. That's why they always have a 1 left shifted by, for example, bit 7. Bit 7 is not actually a defined value in there, but I'm just referring to this. It would also be possible to define them as bit 7, instead of being a 7, could be an 80, and then you wouldn't need to do this one shifted. But I'm afraid that's the way that they've done it. And if you look in the instruction set, look at the way that they do this nomenclature. You see here as well, so here load SPM CR val is being loaded with a 1 left shifted by PGWRT, which is defined. They've used a plus instead of an or. Usually this is a vertical bar. And a 1 left shifted by SPMen, which is store program memory enable. So that is the way that they do it, and the reason why they do it that way is so you don't have to put a comment after it to say what you've done. The instruction itself becomes self-documenting. So we were talking about these two instructions. So the first one is bit 0, that one. It has a value of 1. We did set a value of 1 into it, remember. R22, we set a value of 1, so that's the OX1. This instruction SBR can write lots of bits in, as many as you want. The instruction that tests it is only testing 1 bit. So it's skip if bit register set 22 and bit 0. So it's only testing 1 bit, so you only have 1 number in there. When it is set, it'll jump over this idle, and then we need to do a clear the bit register. Remember, we set it. So what do we put in here now? It's the same thing. We put in clear bit register 2201. And having done that, it'll go back to idle and it'll sit there jumping. So, shall we test it? It jumps to main. It goes through all the stuff that we did in the last session. It sets up the register. And it gets down here. It says, skip if the bit register is set, 22.0. Now let's have a look at 22. It's set to 0, so that bit is not set. So it doesn't skip, it goes to the jump, and it jumps back to idle. And it sits there, just going backwards and forwards, but remember, all the time it's doing this, it's generating clock cycles, and the timer is counting. There, did you see the red blob? Another one. So there, that timer is busy counting up. Now if I put a 7 Charlie in there and just count it up until it goes to 7 dog. 7 dog is what we have in the output compare register. So at this point we'll get our interrupts, or we should do. So as soon as it overspills that, all of this gets reset, and if I execute one more clock cycle, there it goes to the interrupt. It does an R jump and it goes to the handler. It stores the SREG. Now the status register, we've got the Z bit set, the Z bit, the 0 bit. So it'll put that into R15. Have a look down here at R15, and there it goes in. It's put a value of 02. It does some stuff here, we'll get to that. It sets this bit into R22. Have a look at R22. There's the bit gone in. It does some more stuff that I've put in just for demonstration, and now it does an output to the status register of R15. You'll see that the status register, we did have the 0 bit set, and it's not set anymore. So this is the reason why we've got to restore it. When you restore it, that puts the 0 bit back in, and we do a return from interrupt. There are 2 returns. If you go to a subroutine, you do it with an R call, and you do a return from the subroutine as an RET. The return from interrupt is RETI. And it goes back it will set this bit. Now this is the point where we have actually detected that the end of the millisecond has happened, because it jumped over this. So we've now got down into our program proper. We haven't got much of a program at the moment. The only thing it does is reset that bit. But if you look down here at R22, it's a 1 at the moment, and there it goes to a 0, and then we'll start going back to idle. Now if I set a breakpoint at that point, and I reset the cycle counter, unfortunately you can't see this drop down menu, but I've done a screen capture and it does come out on the screen capture, so I'm just going to put that in. Reset the cycle counter. I'll just put that screen center in, that frame in for a second, so you can see what I'm seeing. Although I do hope that you have downloaded this program, the Studio 7, and that you're looking at your own PC and you can see this anyway. But anyway, here's the frame. Right, I'm back again. Now, if we set a breakpoint here, so if I execute F5, it's gone to the breakpoint. I have reset the cycle counter here. I've reset the stopwatch. If I press F5 again, it should get back here again in 1000 milliseconds, right? Ah, can you see a problem? It says 1007 milliseconds. Well, maybe there was an extra few cycles used somewhere. So, but if we repeat that, it should be 1000 milliseconds each time. And it's not. It's going up by more than 1000 milliseconds every time, isn't it? Any thoughts on that? Well, if we set this here, Seven Charlie, and I just step it until it goes to 7 dog. Now at this point I'm going to reset the counters here. Now I'll continue to step it, and there it's gone to 0. There it's generated our interrupt and it's gone to 0. And over here we've got 12 microseconds, and that's from the time that it reached a count of 7 dog. So it spends quite a long time in there, and it only generates the reset at the time that it goes to 7 easy. So what do we do about it? Well, if we wanted to reset at the moment that it gets to 7 dog, then we need to reduce the 7 dog by 1. Here we've got a load register 17 with a 125, which then goes into the output compare register. If we reduce that to 124, which will be 7 Charlie, then if I compile that, F11, I could have gone F5 and it goes directly to the breakpoint. I'm going to reset the cycle counter, so that we've got 0 cycles and 0 microseconds. Now if I press F5, it's gone 998, so it's a little bit less. I don't have a ready explanation for that, but watch this. 2000, 2999, that's near enough 1000. 3998, that's near enough 1000. 5000, so 6000, 7000, 8000. It's trying to do it every 1000 milliseconds, but something is taking a little bit of extra time. There's an extra few cycles being used somewhere. It's probably because the jumps are 2-byte instructions. But you can see that if I hit this 100 times, it'll be very, very nearly 100,000 microseconds. So there I've hit it 50 times, and it's 50,000 microseconds. So our timer is keeping time. We are generating the interrupt. Now then, I'll take that reset away, that breakpoint away, and I'll put a breakpoint in the routine here, because I want to step through this and just show you the stuff that I put in for demonstration. It is convention that registers 16 and 17 are used as general purpose registers. There are a few conventions about how you use registers. If you're writing to memory, you usually put the data that you want to write into memory into registers 0 and 1. And the reason for that is there are some of the memory handling instructions that will only use those two registers. For anything that needs immediate values, you have to use registers above 16. Now you can use 16 and 17, your general purpose registers. You could use registers 18, 19, 20, 21, 22, etc. as general purpose registers. In fact, all the way up to 31 you can use as general purpose registers. They'll serve that function. But it is convention that we use registers 16 and 7 as general purpose. In other words, you're going to load a value in there, you're going to use it for a moment, and it will quickly become irrelevant what's in there, because if anything else is going to use those registers, they won't depend on a value that's in there, they'll be setting a value in. So typically, if you want to load a register lower than register 16, then you would load the value into register 16 and then transfer it to register 4, for example. So it's quite conceivable that you would use register 16 and 17 in your interrupt routine. If you do that, you need to save them first, because you need to restore them before they go back to the program, because something in the program might be using them. So down in the setup here, I wrote two instructions in there: load Y high with a 0, 1 and clear Y low, which is the same as load Y low with a 0. Now your Y registers, we have 3 special registers that can be used for addressing memory. There's the X register, which is R26 and R27. They're all 2-byte register, 2 register pairs. The Y register is 28 and 29, and the Z register is 30 and 31. Y high that we loaded in there, the 0, 1, there's your Y high is 29 and Y low is 28. That's just the way the processor works. Now, back up in the routine here, we are going to store register 16 at the Y register plus 2, and the Y register is actually pointing into memory. So if we go into memory there, not the program memory, but the RAM, register 29 is 01, that's the high, the low is 00, so it's pointing at location 0100, pointing at location hex 100, which is there. So it's going to store the register 16 into Y plus 2, so that'll be over here. You can see that it's already been through this loop. 16 is 10, 17 is 7 Charlie, and it is it stored them in there during the previous loop. So we do oh, in fact, what I can do just to show you is to set these to 0. Now when I execute that, R16, there we see the 10 get loaded into location 102, and R17 gets located, gets written into the next location. We do a move of R1 into R17. Now R1 has got a value of 0 in, so 17 gets a value of 0, and it does. And we increment R16 just for the sake of messing it around a bit. We get down to load 17 with a y plus 3, so it's load with displacement y17, and it comes from 103, so register 17 we see there gets its 7 Charlie back in it, and now we're going to load register 16, and register 16 becomes 10. Then we do our return. So that's our interrupt routine. I just wanted to demonstrate those to you, because in an interrupt routine you may need to save those registers, and well, you've got a lot of memory there to save them into. Right, now we need to develop the ISR, interrupt service routine. You'll find that on the forums they always talk about an ISR because they're writing, so it's much easier to write. Right, a little bit of time has passed and I have modified the interrupt routine so that it now gives status at the end of a quarter second and at the end of a half second. So here we load 16 from Y register, which is pointing to location 100 plus 2, so 102, and into there I have written a Fox alpha which is 250. That's down at the end of main here. After I wrote the Y register, I have then used it to write 250 at Y plus 2 and at 2 at Y plus 3. Remember that the interrupts your program every millisecond. So when it has counted down 256 of them, that's the end of a quarter of a second. And when it has counted down 2 quarter seconds, that's the end of a half second. So back a bit in the interrupt routine, there we load R16 with the count for quarter second. We decrement it and we store it back into memory. When we store it back into memory, that operation std, if you look at the instruction sheet, it tells you that for std, this is all the description of it, and it tells you that it doesn't alter the status register. It's quite important that this store doesn't alter the status register, because it means that we can do the decrement of R16, which may generate a 0 bit if it is decremented down to 0, and that's what we're going to branch on. Obviously, if we're going to do the branch not equals after we have done the store of register 16, then the store itself mustn't alter the status register, and as you've seen, it doesn't. When that value goes down to 0, we drop through this branch not equals and we set a flag. In R22 we set flag 2. So this is going to be end quarter second. This one is going to be end a half second. So you can read through this yourself. It does a similar sort of operation. We initially set 256 into there, and we set a 2 into there. So 256 milliseconds will give a quarter second, and 2 quarter seconds will give a half second, and we will eventually drop through this routine and set flags for quarter second and half second. Now, most of the time, remember, it hits this routine every millisecond. It's got to hit it 256 times before it fails to do a branch not equals to the end of the routine here. So the very worst case of this is where it executes all of the instructions in here, and that's going to happen when we have a 0, 1 in there and a 0, 1 in there. So when these are both going to decrement to 0, it should execute all instructions in the routine. And it'll only do that once every half a second, so only once every 500 times it visits this interrupt. In that particular case, let's just reset the cycle counter and the stopwatch, and we'll step through this. It should fail this branch not equal. It does, because the variable has just been decremented down to a 0. It should fail this one because the half second has just been decremented down to a 0. So this is the one scenario, 1 in every 500 times that it goes through the entire routine. There it restores the register. It loads R16 with what it was before. It restores the status register, and it's just ready to return, and it has taken 30 microseconds. If you are writing an application that requires your interrupt routine to be very fast, then this system of storing everything in memory may not be good for you. If you have enough registers to do it, you can simply keep all your variables in registers, and you can decrement a register much faster than you can recover a value from memory, decrement it, and then restore it to memory much quicker just to decrement a register. Alright, so now if we take that breakpoint away, and I have set here to stop on R22.2, and you'll remember that that is the one that we set for a half second. 22.2 is the end of a half second. So if I run it down to that point, we reset these values, and I press F5 again to go to the next breakpoint, which is the same one, but it's going to take a little while to get there. And we look here, it's taken 499,999 microseconds, which seems to be a microsecond short, but in actual fact this is some artifact of the program, and I'm not quite sure what's doing it. But if I press F5 again, you'll see that it goes to 999,999. So it has taken exactly half a second to get to that point. If I press it 2 more times, 1, 2, now it has gone to 1,999,999. So it's taken another second to do these 2 half seconds. So that is keeping accurate time. For some reason, the first one is always 1 microsecond short, and I don't know what the reason is, but I don't think that it's important. So if you were to change this to 1 and this to 2, then we'd be getting an interrupt. Then we'd be breakpointing it every quarter second. Right, let's program a chip. That's my computer. That's my breadboard plugged into one of the USB outlets on my computer. That's the cable that I use for my programmer. There it is. And that goes in there, and the programmer lights up a little light to say hello. So the chip is currently on the breadboard, so let's take it off. There it is, and I put it into the programmer, always being careful to note where pin 1 is, because if you put it in backwards you'll cook it. So there it is in the programmer. Plug it in. To program the chip, we first of all want to come out of here, Control Shift F5,
to come back to the programming state. The program is already compiled because we were just in the debugger. But if it wasn't, if you press F7, that will compile it. And there you see build 1 succeeded or up to date, no failed, no skipped. And to program it, under Tools, in the command box you need to have your disk location for the AVR dude program. And in the arguments box you need to have the parameter string to be passed to AVR dude. The title will be used in just a moment to select the programming operation, though you won't see it, it wasn't recorded by this screen recorder. You have to be on the right port, so I'm currently on port 6, and you can see that by going to Control Panel, Device Manager, Ports. If you don't have a ports line there, it's because you haven't got anything plugged into one. And there's my device there on COM6. So now we go Tools, Arduino Nano COM6, that's the title. It brings up a command box and it does the program, and it's pretty quick. Much quicker than the Arduino IDE. So that's it, the chip is programmed. So now we unplug that, because you never like to unplug chips with power on. Take the chip out. Always make sure where pin 1 is, because, well, I've done it before. If you plug it in backwards, they die. Plug it into the breadboard and let's try it. And there's LEDs running around in a ring. Taking about a half a second per LED. Now going back to the diagram that we had, we can see that we can light these LEDs in banks, those 3 or those 3, and we can light them in pairs, those 2 or those 2, or we can light the whole lot. But there are some combinations that we can't have. We can't, for example, light only LED 3 and LED 4. Lighting LED 3 would mean having this line low, lighting LED 4 would mean having this line low, and if you had LED 3 lit, then LED 6 would also light. If you had LED 4 lit, LED 1 would light. But there is a way that you can do this, and I'll come to that in the next chapter.